Welcome to the 25th lecture of combinatorics. So, in the last class we were discussing linear homogeneous recurrence relations. I repeat what this thing was. So, we are talking about a sequence like H0, H1, H2, H3 and so on. So, the recurrence relation is told it's called linear homogeneous recurrence relation of order k if the nth term can be expressed in terms of at most so the k previous terms. I mean at most k means you do not have to use all the k previous, but you should know should not go below k, right. So, it is something like this. So, C1 times h n minus 1 plus C2 times h n minus 2 plus like that C k times h n minus k. So, we are using this h n minus 1, h n minus 2 up to h n minus k, combining them in some fashion to get the new term h n, right. So, you should note that when I say this is of order k, this recurrence relation is of order k, what we mean is there are the lowest term we are taking is h n minus k. So, which means that we are assuming c k not equal to 0 here, because if c k was equal to 0 we could have stopped saying at the previous point, right, c k minus 1 times h n minus k plus 1, right. Then we can say that we have used only at most k minus 1 previous term starting from h n minus 1, right. So, therefore, to say that it is of order k, we should make sure that c k is not equal to 0. So, these terms can be 0, cannot be 0, may or may not be 0, right. And also note that this is called a linear recurrence relation, because so in each of this term we are only using h n minus 1, h n minus 2, etc. We are not combining them. For instance, no terms of this form h I into h j, right. So, or h I square, such terms are not used. So, therefore, in that sense it is linear. And finally, the homogeneous recurrence relation, because we do not have the constant term, right. So, that means sorry, not constant term, so a term which does not involve any previous terms. So, we wrote h n equal to c1 times h n minus 1 all the way up to c k times h n minus k. So, in general, if it is just linear, the homogeneous word is not there, then we can also have a b n here, right. So, in the homogeneous case we do not allow this b n, right. So, b n has to be 0 for homogeneous case. Non-homogeneous case b n can be non-zero. Then note that the c i's, these coefficients for this h i's, so they can be constant. If they are constant, then we say that this recurrence relation is a linear homogeneous recurrence relation with constant coefficients, and but it in general it need not be. So, it can be a function of n, right, it can be a function of n. So, for instance, it can be something like here n square times h n minus 1. So, right, for instance, if I write a recurrence relation for factorials, I will write h n equal to n into h n minus 1 with h 1 equal to 1, right, h 1 equal to 1, h 0 is equal to 1, right. So, so here the coefficient is not constant, it depends on n, it's a function of n. But when we will be studying mostly the recurrence relations where these coefficients are constants. So, and then there is yeah, right, these are the main points. So, we wanted to tell, and also note that, so this relation can only be true for n greater than equal to k, because we are using k minus 1 previous terms. So, from kth term onwards only we will get k minus 1 previous terms, sorry k. So, we are using k previous terms. So, there should be the n minus kth term available, right. So, from kth term, so this is k, n equal to k case, k minus k will be 0. So, we are starting from h 0. For instance, if you had tried to write this expression for h k minus 1, so that would be a problem, because h k minus 1, so the c k times h k minus 1 minus k will come here, which would be h minus 1. So, which is not defined, because our sequence starts from h 0, h 1, h 2 like that, right. So, this relation is valid only for n greater than equal to k. These are the main points about this kind of recurrence relations. Again, linear homogeneous recurrence relation of order k, and then constant coefficients. This that is what we are going to study from now on, right. So, now the next thing is to see how a general solution can be obtained for this thing. So, the key technique we are going to learn is like this. So, we will learn. So, we will introduce a notion called the characteristic equation of the recurrence relation. What is the characteristic equation of a recurrence relation? So, for instance, if the recurrence relation was h n equal to 2 h n minus 1 plus h n minus 2, say, then so we can suppose, so we can guess that q. So, let q be some number, and suppose we guess that so the solution for this recurrence relation will be of the form q to the power n. Suppose we guess like that, and then you substitute here q to the power. Suppose it is like that. I do not know for which q it will be satisfied, or whether it will be satisfied or not. So, we substitute and try whether it will work out or not. So, h n will become q to the power n. So, when I say h n will be equal to q to the power n, what we mean is h 0 equal to q to the power 0, h 1 equal to q to the power 1, and h 2 is equal to q to the power 2, and so on, right. So, if that is the case, then for this h n equal to 2 h n minus 1 plus h n minus 2, when I substitute this q to the power n here, and then this will become 2 into q to the power n minus 1 plus this is q to the power n minus 2. Now, we will assume that q is non-zero, q not equal to 0. Then we can cancel on both sides, or in every term, q to the power n minus 2. So, that will become q square, because q to the power n minus 2 is gone, 2 into q plus 1. That is what is coming, right. This goes away, this goes away, and here we have 2 q left, and here we have q square. So, this is the thing. Now, we know that, so any q which satisfies this equation x square minus 2x plus 1 equal to 0, sorry, say x square minus 2x minus 1 equal to 0 will satisfy this equation, and we know we can solve for this thing by the usual techniques, and those, so there will be you can use it the formula for solving the quadratic equation, and those values can be given to q, and this will be satisfied. Now you notice that by our argument, if this is satisfied, so again I will at this point we will say this is the characteristic equation of the given recurrence relation, and if a particular value satisfies this characteristic equation, then of course, so this is satisfied. That means this original q to the power n 2 into q to the power n minus 1 is equal to 2 into q to the power n minus 1 plus q to the power n minus 2 will be satisfied. That means for this recurrence relation, this Hn equal to q raised to n is indeed a solution. That means if you substitute Hn equal to q raised to n for that particular value of q is obtained by solving this characteristic equation, right, it will be satisfied. So this recurrence relation will be satisfied. The only worry is that there will be some initial condition which may not be satisfied. You know that q to the power n, right, with that particular q which is coming from this equation, so we will satisfy the 2 into q to the power n minus 1 plus q to the power n minus 2 solution, but we also need that h0 is equal to certain thing. So in this case, you know, in this recurrence relation is written for all n greater than equal to 2, right. So h0 equal to something, h1 equal to something, we will have two initial conditions for this kind of a recurrence relation. The point is we have to make sure that these initial conditions are also satisfied by our solution. So if you just take that the root of this equation, characteristic equation, and say that let that be q, so we take that q to the power n and then put n equal to 0, that will be q to the power 0, this will be h0. So this has to match our initial condition that h0 is equal to a. Similarly, if you put n equal to 1, q to the power n will be h1, that has to be equal to b. So this may not happen all the time, right. So we should develop some techniques for that. So the trick is this. So we will say that okay, q to the power 1 is a solution. So suppose we have suppose let's look at the characteristic equation here, x square minus 2x minus 1, right. So if I had solved it, that will be minus b plus 2 plus or minus b square minus 4ac, that is 4, sorry, the solution is minus b plus or minus b square minus 4ac by 2a, 4, this kind of a solution, ax square plus bx plus c equal to 0. Now in this case we have a equal to 1, b equal to minus 2, c equal to minus 1. So this will be 2 plus or minus, so 4 minus, because a is also minus 1 here, so minus 4ac will be just 4, right, plus 4 by 2 into 1. So this is what this will be 2 plus root 8 by 2 and 2 minus root 8 by 2. These are the two solutions, right. So now if you take q is equal to 2 plus root 8 by 2, that means 1 plus, you take 4 out from here, root 2, right, 1 plus root 2. Or similarly, see what I do is I can take I can write this portion as 2 into 2 plus 2 into root 2, okay. Similarly this is 2 minus 2 into root 2, so I cancel off 2. So this is this q, and let's say other solution is r, so that is 1 minus root 2, right. These are the two solutions. So, so now when I take put q equal to 1 plus root 2, that will indeed satisfy the recurrence relation, but not necessarily the initial condition. In general, the initial condition can be see q raised to 0 equal to h 0 equal to some a, right, some a, maybe we can say this is equal to 10. Similarly, q equal to q raised to 1 equal to h 1 is equal to something, it can be 5 whatsoever, I mean, or maybe so this is given as part of the problem. So, we cannot control this thing, right. So, then we get that, for instance, if we have taken q equal to this one, the first 1 plus root 2, we will just get 1 plus root 2 to the power 0 is equal to 10, which is not true, because this is definitely wrong. Similarly, 1 minus root 2 to the power 0 is equal to 10 is also wrong. So, both choice of q, so either we take the solution 1 plus root 2 or 1 minus root 2, both are not valid for the initial condition. How will we tackle this situation, right? So, the answer to this question is that, suppose, so let us say q, I will write q1 equal to 1 plus root 2 and q2 is equal to 1 plus 1 minus root 2, these are the two solutions. So, we will notice that our recurrence relation hn equal to 2 into hn minus 2 plus hn minus 1 will also satisfy any combination of these solutions. That means, if I had taken C1 times q to the power n plus C2 times q to the power n as a possible solution for Hn, that would also be satisfied, that is also correct, because if I substitute Hn equal to this and Hn minus 2 is equal to C1 into q to the power n minus 2 plus C2 into q to the power n minus 2, and Hn minus 1 is equal, sorry, Hn minus 2 is equal to C1 into q to the power n minus 2 plus C2 into q to the power n minus 2, then also this will be satisfied. Why is it so? Because you just have to substitute and see, because on this side, so in this case, in this special case, I will show the substitution. So, for instance, in the when I substitute for this Hn, so what we get is C1 into, so here C1 and C2 are just some constants. So, C1 raised to Qn plus C2 into Qn, this is what, this will be equal to 2 into C1 into Q raised to, so this is Q1 Q2 Q1 raised to n and Q2 C2 Q1 raised to n plus C2 into Q2 raised to n. See, what I am trying to do here is I have two possible solutions, Q1 raised to n and Q2 raised to n. So, now I am saying that if I had taken some constants, two constants C1 and C2, and cooked up a new solution, Hn is equal to C1 into Q1 raised to n and plus C2 into Q2 raised to n. This would also be a valid solution for our recurrence relation. So, this is a very simple fact, because see, if you substitute it here like this, right. So, this will just be like C2 into Q2 raised to n minus 2. Now, combining things, this says Q1 raised to n1 on this side. So, I will only consider the terms involving Q1 raised to n. So, here we have Q1 raised to n. So, here we have Q1 raised to n minus 1, here we have Q1 raised to n minus 2. So, here this is C1 into Q1 raised to n, here it is C1 into 2 times Q1 raised to n, here C1 into Q times sorry, C1 into Q1 raised to n minus 2. So, now we know earlier we know that if C1 was not there, C1 is just a multiplier on both sides, Q1 raised to n is indeed equal to 2 times Q1 raised to n minus 1 plus Q1 raised to n minus 2, right. So, that is still correct, we can substitute with that here on this thing. So, just C1 is another multiplier. So, both sides we have C1. Similarly, Q2 raised to n is equal to 2 times Q2 raised to n minus 1 plus Q2 raised to n minus 2, and we have the extra multiplier, the C2 on both sides, therefore, they just cancel off, right. So, if you have any confusion in this discussion, I will put it like this. We already know that Q1 raised to n is equal to C1 raised to, sorry, forget about C1. We already know that Q1 raised to n is equal to 2 into Q1 raised to n minus 1 plus Q1 raised to n minus 2. This is equation 1. Now, similarly, we know that Q2 raised to n, because this is also, Q2 is also a value which is obtained by solving the characteristic equation, is Q2 raised to n minus 2 plus Q2 raised to n minus 2, right. Now, you can simply multiply this equation 1 by C1. So, here it will be C1, C1, you can multiply by C2 here, C2, C2, C2. Now, add it together. So, this will become C1 raised to Q1 raised to n plus C2 into Q2 raised to n, right. This was the proposed solution for Hn now, right. And now, if you multiply it here, you will get 2 times C1 raised to Q1 raised to n minus 1, C1 into Q1 raised to n minus 1, C2 into Q1 raised to n minus 2, and this portion is the Hn minus 1 according to our new solution, right, new proposed solution, right. Here if you, when you multiply it, C1, this is C1 into Q1 raised to n minus 2 plus C2 into Q2 raised to n minus 2, right. This is the proposed solution for Hn minus 2. So, this is indeed Hn is equal to 2 into Hn minus 1 plus Hn minus 2. So, this also works. To summarize, what we are saying here is, if Q1 raised to n is a solution and Q2 raised to n is a solution, for any two constants C1 and C2, C1 times Q1 raised to n plus C2 times Q2 raised to n is also a solution, right. But what is the good about it? So, we cooked up all these things. The good thing is these C1 and C2 are two constants which we are free to select. C1 and C2 are two constants which we are free to select, right. And we can select those constants in such a way that the initial conditions are satisfied. So, it is something like this. So, for instance, C1 into, so in our case it is 1 plus root 2 raised to n plus C2 into 1 plus root 2 raised 1 minus root 2 raised to n, right. If this is the equation, sorry, this is the new solution proposed for Hn. So, we are claiming that for any C1 and C2 this is correct, that is what we have seen there, right. This is the recurrence relation will be satisfied. That means, recurrence relation is 2 into this relation will anyway be satisfied, right. The only thing we are worried about is the initial condition, namely when n equal to 0 what will happen. When n equal to 0, this will simply become C1 plus C2 is equal to. So, if it was 10, we can write it like this, right. And then the next thing, so when n equal to 1, what will happen? C1 into 1 plus root 2 raised to 1 plus C2 into 1 minus root 2 raised to 1 is equal to, if you put what was the thing we put here, 5 suppose, right. So, we will get like this, right. Now, we know that this can be solved, these are simultaneous equations, and you know this is definitely not a multiple of this thing. So, you can try to solve it. So, I do not waste time solving it here, right. So, now you see that the advantage is now you can get values for C1 and C2 here by solving these equations such that these initial conditions are indeed met. When you put n equal to 0, this proposed solution that is H0, right, will indeed be equal to the given value 10, right. Similarly, H1 when n equal to 1, they will indeed be the value say 5, right. So, because we will be selecting the constants in such a way, right. This is the technique. Again, once I summarize what we have done as, so we introduced this concept of characteristic equation. That means this was by, we wanted to make sure that for some q, right, q to the power n will be a solution for that recurrence relation. For that thing we cancelled the term say q to the power n minus 2 from both sides after substituting q raised to n for Hn or q raised to n minus 1 for Hn minus 1 and q raised to n minus 2 for Hn minus 2. And then we got one equation, is a quadratic equation because we only had maximum q to the power 2 there, and we solved that quadratic equation and got the two possible values which will work for that. That means if those two values are used for q, then indeed that recurrence relation will be satisfied. Then we saw that the only trouble was about the initial condition. Now, when you put n equal to 0, we are getting some value for once, say one of the solutions of that characteristic equation was taken for q, and that q to the power 0 was not necessarily equal to the H0 value we are given, right. Similarly, if you try the other route of that characteristic equation, even then it may not work. Now, to the solution now was to note that if q1 raised to n is a solution for Hn and q2 raised to n is a solution for n, that means if they were satisfying the recurrence relations, then C1 times q1 raised to n plus C2 times q2 raised to n also will satisfy. So, we showed it by explicitly writing two equations, multiplying by C1 one of them and C2 by C2 the other equation, and then adding them together. We showed that is indeed the case, and therefore, so we can think that this is the solution for this thing, right. So, for instance, if you substitute this in the recurrence relation for any value of C1 and C2, it is working out. Now, we just match, put n equal to 0, then see what is happening. It was just C1 plus C2 equal to something, right. And similarly, put n equal to 1, we get some equation. So, we get a simultaneous equations, two simultaneous equations in two unknowns, namely C1 and C2. We wanted to figure out for which C1 and C2 these initial conditions will be met, and we can get that, right. Now, we will generalize this thing. See, I used a small recurrence relation, means order when the case where k equal to 2, that means a recurrence relation of order 2 to illustrate this thing. Right, it is easier to explain, that is why it was selected, but we can do it for order k case without much difficulty, right. So, that is what is written in this thing. So, here we are considering a recurrence, general recurrence, linear homogeneous recurrence relation with constant coefficients. So, now we can rewrite the recurrence relation is Hn minus a1 times Hn minus 1 minus a2 times Hn minus 2 until ak times Hn minus k equal to 0 with, so here I should have put 0. So, with ak not equal to 0, n greater than equal to 0, and then the corresponding characteristic equation will be x raised to k into a1 into x raised to k minus 1 minus a2 into x raised to k minus 2 minus up to ak equal to 0, right. This is the characteristic equation. So, I can make it clear here. So, we first rewrite that recurrence relation, general recurrence relation like this. This is the thing, because H1 equal to this, we brought all the terms from the right hand side to the left hand side. So, here the conditions were ak not equal to 0, and this what is written here will work only for n greater than equal to k, right. Now, we just guessed that Hn equal to q raised to n. For some q we have to decide will be a solution for this thing. Now, we substitute it, we will get something like q raised to n minus a n minus 1 q raised to n minus 1 minus a n minus 2 q n minus 2 all the way a n minus k times q raised to n minus k equal to 0. You can cancel off q to the power n minus k. We are assuming that q not equal to 0. We will select some q which is not equal to 0. Right. Now, so we can cancel q to the power n minus k. We get q to the power k then, right, k minus a n minus 1 q to the power k minus 1 and plus here a n minus k is equal to 0. And you can see that this means q is a solution of this following equation, namely x to the power k a n minus 1 into x to the power k minus 1 plus a n minus k equal to 0. And this equation is the characteristic equation, x to the power k minus a n minus 1 x to the power k minus 1 plus a n until a n minus k equal to 0. It is easy to get, one does not have to memorize it, you just have to follow this procedure and you easily get it, right. X to the power k minus a n minus 1 x to the power k minus 1 plus up to, sorry, this is minus here also, so minus. This is going to be the, everything is minus here because all terms are minus, okay. So, this is going to be the characteristic equation. Now, of course, we have to find the roots of this characteristic equation. This is a degree k polynomial here, and that is equal to 0 is what you are saying. It may have, it will have k roots, right. So, you can take any root of it, say q is a root. So, it is clear that this equation will be satisfied by q. So, that means q raised to k minus a n minus 1 raised to q raised to k minus 1 minus is that a n minus k is equal to 0 will be true, right. You have to take a non-zero k. Now, yeah, if you get so we will consider the situation where this characteristic equation has all non-zero and distinct roots and non-zero right, all are non-zeros and distinct. Then we can also see that, as by the same procedure we did in the case of order 2, we can select constants C1, C2, Ck, sorry, not necessarily C1, C2, Ck, that is this constants. So, here we are, right. So, this constants are n minus 1. So, we can use some constant C1, C2, Ck Actually any constants will work, right, it does not matter which constants you select. So, and if you combine the solutions C1 into Q1 raised to n plus C2 into Q2 raised to n plus Ck into Qk raised to n, then this will also be a solution. This is nothing surprising. You see, when you substitute Q1, this kind of an equation is valid, right, and then when you substitute Q2, then also Q2 raised to k minus a n minus 1 into Q2 raised to k minus 1 minus a n minus 2 into Q2 raised to k minus 2, like that, minus a n minus k equal to 0 is valid. Now you can multiply the first equation by C1, that is still valid, and then you can multiply the second equation by C2 and so on and add them together. So it will be indeed correct, right. So and you should also note that here when I say non-zero solutions, that is not very important, because for this characteristic equation, so it's a characteristic equation. So here it is Hn A1 to Ak, sorry I made a mistake here. So H1 minus A1 raised to Hn minus 1 minus, so Ak, because see I was just trying to use the same subscript as this thing, but our notation says the first coefficient is A1 and H2, that is the way we have written here, right. So everywhere 1 2 okay. Okay. Right. So now if in this characteristic equation you remember this Ak is not 0, sorry, in this equation, in this recurrence relation, Ak is not 0 by our assumption. Now when you write this thing, so after dividing by q raised to n minus k, we get an equation where this constant term is not 0. So q equal to x equal to 0 will not be valid for this thing. So x equal to 0 is not a solution of this thing. So the solutions will indeed be non-zero, right, solutions will be indeed 0. So this is not required, we can just assume that they are all non-zero, right, because that is the way we have set up things, because our coefficients were selected in such a way that, so we had the assumption that Ak equal to non-zero, right. So therefore there will be the constant term there which is non-zero, so therefore x equal to 0 will not be a solution for that, right. Now we just have to say, suppose there are all the roots are distinct, right, C1 C2 Ck. So now we can combine the solutions q1 raised to n. So Hn equal to qi raised to n is a solution for each of these k roots, where qi is the ith root, okay. So that is what it is, because it is a root, it should be a solution that it should satisfy the recurrence relation. So it is clear, right, because that is the way we have set up this thing. Now we also seen that we can combine it this way, and this is also a solution, because Hn, if I substitute Hn equal to this, right, in that recurrence relation, it will be satisfied. The good thing about this thing is that, so here we have this coefficient C1 C2 Ck, right, C1 C2 Ck, and these coefficients see, as of now it can be any constants. Now we use that freedom to match the initial conditions. How many initial conditions will be there? We will have H0 given, H1 given, H2 given, up to Hk minus 1 given, because our recurrence relation is valid only for n greater than or equal to k. So this initial condition should be given. So what we do is we substitute n equal to 0. So when you substitute n equal to 0 in that characteristic equation, I write the characteristic equation here once again. So, this is x raised to n, x raised to k minus a1 raised to x raised to k minus 1 minus a2 x raised to k minus 2, finally minus x a k equal to 0. This was the characteristic equation. Now, put n equal to 0. So, this is the characteristic equation. So, now we are saying that, so this characteristic equation will be satisfied by, so any of the solutions q1, q2, qk of this characteristic equation, and we are assured that none of these are 0 because a k is not 0, and we noted that then the recurrence relation should satisfy should be satisfied by a solution of this sort, C1 into Q1 raised to n plus C2 into Q2 raised to n plus Ck into Qk raised to n. Now, you put n equal to 0 in this thing. What do you get? So, you get C1 raised to Q1 raised to 0, that is just 1, plus C2 into Q2 raised to 0, that is again 1. So, Ck is equal to something. This can be the value of the, so this is H0, right. Now, put n equal to 1, you will get C1 raised to Q1 plus C2 Q2 plus Ck Qk is equal to H1. Now, put n equal to 2, we get C1 Q1 square plus Q2 square plus Ck Qk square is equal to H2. Like that, when you put n equal to k minus 1, we will get C1 into Q1 raised to k minus 1 plus C2 into Q2 raised to k minus 1 plus Ck into Qk raised to k minus 1 equal to Hk minus 1. So, we want to find values for C1, C2, Ck such that all these equations are satisfied. This is the first equation, this is the second equation, so the kth equation, the k equations, right. Is it possible always? So, then we say that it is a general solution. The word general is used in the sense that irrespective of the initial conditions, we can find these coefficients C1, C2, Ck such that the solution C1 into Q1 raised to n plus C2 into Q2 raised to n plus up to Ck into Qk raised to n will indeed be a solution for the recurrence relation. The initial conditions will be met and the recurrence relation will be met. So, can we always find values for C1, C2, Ck? So, if you remember from linear algebra, this will correspond to solving this matrix equation Ck equal to H0, H1, Hk minus 1. So, this is 1, 1, 1, 1, 1, and this is Q1 raised to 1, Q2 raised to 1 up to Qk raised to 1, and this is Q1 raised to 2, Q2 raised to 2, Qk raised to 2, and finally this is Q1 q1 raised to k minus 1 to qk raised to k minus 1. So q2 raised to k minus 1, so on. So this is a k by k matrix, and the question is, do we have a solution for this? So can we find values for C1, C2, Ck such that for any value of H0, H1, Hk minus 1. So we know from linear algebra that this is possible when this determinant is non-zero, and this is, so we do not get into the details of this. So it is known in that this matrix, which is called the Van de Monde matrix, indeed has a the determinant is indeed non-zero, right, because the determinant of this matrix is known to be product of, for every pair I ij qi minus qj, this is what the determinant of this thing qj. So we write like this, k, right, there are k q values here, right. So q j minus qi, this is the determinant. Note that here we are assuming that all roots are distinct. So that means qi is never equal to qj. So this qj minus qi is never 0. So this will evaluate to non-zero. So this determinant is non-zero, right. So this matrix, so I am not, see this matrix is Van der Monde matrix, and this is a very famous matrix, and you can check some linear algebra books to verify that this determinant is indeed this. So because we want to save some time, that is why we will not get into the calculation of that. And also here there is some linear algebraic ideas are used, namely, so here this linear equation, system of linear equations is converted to this matrix equation. So that is Ax equal to b kind of equation, which is, you should be familiar with this stuff, right. So here instead of x I have written this vector C's, C1, C2, Ck, and then this A matrix is the Van der Monde matrix here, where yeah, so the matrix comes like this. Why the matrix comes like this is because we are collecting the matrix from here. So 1 here, 1, these are the coefficients, C1 into 1, C2 into 1, that is what that one, first row is coming like that. The second row Q1, Q2, Qk, so third row Q1 raised to 2, Q2 raised to 2 and Qk raised to 2, because we are substituting n equal to 2 there, and so that is how this matrix is coming from. And this answer has to be H0, H1, that B has to be, so this is the B here, right. So this is very familiar thing in linear algebra, and then it is known that, so this is indeed a k by k matrix, and this kind of a system of equations will have a solution always irrespective of what B is, right. If this matrix determinant is non-zero, then the matrix is invertible, and we can the inverse of this matrix, with the inverse of the matrix we can multiply by this B. So we will get the solution for this x, right. So this is what, this is some ideas from linear algebra, right. So the only non-trivial thing in this part was just to know whether this matrix indeed has a non-zero determinant or not. Luckily it so happened that it is a very famous matrix, and that matrix determinant is already known, right, though it is not very difficult to work it out, but to save time we can just avoid it, and it indeed requires a lot of knowledge, and then we have to explain all the details. Therefore we would just skip it, right. Interested reader should read it from some other sources, right. So, this is non-zero, and therefore, indeed we can always solve for C1, C2, Ck such that the initial conditions are met. So, now we have already dealt with the general case, right. So, what are the key points? The key points are that, right. So, we were given this linear homogeneous recurrence relation with constant coefficients, and yeah, of course. So, this we found out a way to get some solutions for Hn, right, so that the recurrence relation is valid. So, that is by solving the characteristic equation, and this whatever we have discussed works only when all the roots of the characteristic equations are distinct. We observed that the root, because of our assumption that Ck Ak, the last coefficient we used, Ak times Hn minus k, that Ak is assumed to be non-zero. The this characteristic equation cannot have a zero solution root, it cannot have 0 as root. Therefore, all roots are non-zero, just that we are assuming they are all distinct. In that case, we also noted that when we combine C1 times Q1 raised to n plus C2 times Q2 raised to n, that is also going to be a solution. That is a trivial fact, right. We are just multiplying by the corresponding coefficients and adding together, we show that it is indeed a solution. So, the only non-trivial aspect was to somehow make sure that irrespective of the initial conditions, that means H0, H1, H2, Hk minus 1, these things are given values, it is not in our hands, that can be given any value by the one who writes down that sequence, right, because the rule works only starting from n greater than equal to k, n equal to k onwards only it works. The initial k 0 to k minus 1, h0 to hk minus 1 can be set up in any way. So, therefore, we understood that how will we, the key point was to figure out those constants C1, C2, Ck. So, in that combination C1 raised to C1 into Q1 raised to n plus C2 into Q2 raised to n, such that all the linear initial conditions are met. That we saw that we can write down all the equations by n equal to 0, n equal to 1, n equal to up to k minus 1, and then we showed that always we have solution for that. So, we can uniquely solve for C1, C2, C3, Ck minus Ck, sorry, right. Then once you set those, after solving that, we fix those values for Ci's, and indeed the initial condition will be met and the recurrence relation will be met. This is the technique, right. So, now of course, we can quickly consider some simple examples if you want. Let us look at Hn equal to Hn minus 1, it is a little more complicated. Hn equal to Hn minus 1 plus, sorry, Hn minus 2 minus 2 into Hn minus, Hn equal to 2 Hn minus 1 plus Hn minus 2 minus 2 into Hn minus 3. Just look at once again, yeah, the first, and H0 equal to 1, H1 equal to 2, H2 equal to 2. Suppose this is our reconciliation, not that this first relation will be valid only for n greater than equal to 3, because if you try to write it for H2 n equal to 2, so of course n 2 minus 3 is H negative 1, so that is not defined, right. How will you do this? First you write the characteristic equation for that. So, you recall how to do that. So, assume that for some non-zero q, right, q to the power n is a solution for h to the power n, substitute it and cancel q to the power n minus 3. So, we will get x raised to 3 minus 2 into x square minus so minus x plus 2 into plus 2 sorry equal to 0 as the characteristic equation also. What I did is I took all the terms to this side and then cancelled off q to the power n minus 3 terms. So, that will correspond to q cube minus 2 into q square minus q and then plus 2, right. So, q is a solution for this stuff, this equation, this is the characteristic equation. Now, we can solve for this characteristic equation. If you solve this thing, say let us not waste time trying to see what are the solutions and all. This will give the solutions as 1 minus 1 and 2. It is easy to verify this thing, right. So, that means, so 1 raised to n, so put h equal to 1 raised to n, that will be a solution for this thing, right. So, that means what is this 1 raised to n, 1 1 1 1 like that, right. So, that is indeed a solution. You can see that yeah, you can verify here for if everything is 1, this sequence, right, 1 1 1 1 1 1 1 1. So, h n equal to 1 raised to n is indeed a solution for this thing, right. Similarly, so you substitute it, you can see that it is correct, minus 1 raised to n is also a solution, 2 raised to n is also a solution, and more than that you can select any constant C1, C2, C3 and C1 raised into 1 raised to n plus C2 into minus 1 raised to n plus C3 into 2 raised to n also will be a solution for this thing. That is what we told, right. Now, the work is only to meet the initial conditions, namely h0 equal to 1, h1 equal to 2, h2 is equal to 2. Substitute for n equal to 0, that will be C1 minus C2 plus C3 equal to 1. This is what h0 is equal to 1 gives us. Then sorry, h0 is equal to 1 gives us, h1 equal to 2 will give us C1 raised to sorry h1 1 minus C2. So, I think it is time, therefore, I will finish off in the next class, or maybe I need not do this thing, because this is just a simple thing. You can write the equations for n equal to 1, n equal to 2 and solve for C1, C2, C3 and that will be the solution, right. So, we will start off with something else in the next class.